Hello, welcome back to this series of lectures on microprocessors and microcontrollers. You are watching lectures on 8086 microprocessor. We have discussed in the earlier classes an introduction to the 8086 microprocessor, the pin diagrams, the internal architecture, the programming mode of the 8086. In this video, we will see about the memory organization of 8086 microprocessor. We know that when we talk about any of the microprocessor, we mean that the memory is external to the system. It is not part of the system. When we say system means microprocessor. It is an additional peripheral that is attached to the 8086 so that we can make something useful out of it. In itself, the microprocessor can't do anything unless we have some place where the instructions and the data can be stored. And since any microprocessor doesn't have inbuilt flash or some kind of ROM memory, we have to have every kind of storage device, whether it is the primary or the secondary, as an external to the system. Now, since the memory is an external to the system, we must know how this memory is organized and how we can access this memory. So for this, we have divided this video of the topic into different parts, and these parts are the segmented memory, then the physical address, how the physical address is generated, and then how the memory itself is addressed using the even or the odd word alignments. So before we proceed with the segmentation and the memory concept, it is required to know the pin diagram of the 8086, which gives us certain information about the addressing. We have already seen this particular pin diagram in the previous video, but this video again, we look at this pin diagram from the perspective of the addressing the memory. So when you look at the pins, what do you find here? That the pins A19 and it goes backward A14 and down to A0. So that means 8086 has 20 address pins. Of course, many of the pins are dual function, having more than one function. For example, the lines AD0 to AD7, they carry address as well as the data lines. The upper address lines from A16 to A19, they are also used to carry the status information. So that means those lines which have multiple functions, they are required to be demultiplexed in the external world. So that only we have the address lines and the data lines separately, not multiplexed external to the system. So when we talk about the memory in the real world, which is always external to the 8086, it is in this world that you have to have the memory devices which can be interfaced to the 8086. Interfacing we'll see in the next video. So that means now when we know that the 8086 doesn't have on-chip provision, it only provides the address lines and the data lines and maybe some control lines. So we need to make use of these lines only in addressing the external memory. So we'll be much concerned with the line BHE, bus high enable, when we discuss about the even and the odd address. we have to be concerned with the line BHE bar, bus high enable, when we discuss about the even and the odd memory banks of the 8086. So as of now, let's move to the next slide and see how the memory is addressed by the 8086. What kind of provision 8086 has? We know the 8086 total memory space A0 going up to pin number here 35, which is A19, starting from pin number 16, going down to pin number 2, then moving to pin number 39 and coming down to pin number 35. So these lines are for the address. So if you talk of only the address after multiplexing, demultiplexing, you have the line A0 to A14 at line number pin number 2, then A15 pin number 39, coming down, and pin number 35 is A19. So in all we have 20 address lines on the chip. So with the 20 address lines, we know the total memory space that is accessible by the 8086. The total memory space is, with the 20 lines, 2 power of 20 equals to 1 megabyte. So with the 20 address lines, we can address up to 1 megabyte of memory. But when you peek inside the 8086 and look at the registers, because the purpose of the register is not only to store intermediate results. Some of the results registers, they also store the address of the memory, and they are the pointers or the index or the base registers. But the size of each and every register, as we know, is only 16-bit, but the address is 20-bit. So with only 16-bit, if we use only one register which is 16-bit, it can only take care of 64 kilobytes of addresses. So designers of the 8086, they have made a provision that we hold the address in 2 or more registers. And one of those registers will be called as a segment registers, which will hold the base or the starting address of any of the segments. So the memory, which is 1 mega in size, since it cannot be addressed directly, provision has been made that the memory is divided into different segments. So like extra segment, stack segment, data segment, and the food segment. So this is not a physical division of the memory, it is a logical division of the memory. And each of these segments, as we saw in the one of the video, that they can be overlapped segments or they can be non-overlapped segments. But in any way, there are active 4 segments at any instant of time. Of course, if there is a requirement, because the segment limit is 64 kilobyte, so we can increase by using some other segment as. So like the extra segment can be used as a 4 segment so as to increase the size of the 4 segment, or they can be used in the overlapping. Now, when we know that memory is segmented, and each of the segment has its effective address, which is only the 16-bit address. But with the base value, let us, for example, suppose see that this particular segment starts from address 00000. So starting from here up to 64 kilo will be one segment, and to address the 64 kilo Of course, one register is sufficient, but we have to look for the complete addressing. So one of the address registers can hold some kind of say effective address, or even the effective address can be generated if there are more information about the calculation of the effective address. And that effective address, when manipulated with the base value, let's say this base value is 0000. So the base value multiplied by 16 will append a 0 with it, and then adding the offset value or the effective address value will give us the 20-bit, the physical address of 8086 memory system. But when we talk of the memory, we know the memory is always in terms of the bytes. And 8086 is a 16-bit processor. So is it that we access the memory locations or the data which is in the memory a byte at a time, or is there a provision somehow so that we can access the whole 16-bit of data at a time? Since we have the 16 bits of the data bus available, and also the registers are of size 16-bit. So if we are somehow able to access 16-bit at a time, so it will speed up the operation of the microprocessor 8086. So for that we have a provision of accessing the even and odd memory locations. So for this, the memory is divided into two banks. And what these two banks are called as the bank 0 and the bank 1. So then dividing these banks gives us the advantage that all the odd addresses will point to the bank 0 and all the even addresses will point to the next, that is the bank 1. So that means we are able to have some kind of mechanism, as I said in the while discussing with the pin diagram, that we have a line called as a DHE. So if somehow the two banks are constructed, and we know the total size is 1 megabyte, so half the memory can be even at odd addresses, and the other half may belong to the odd addresses. So supposing now that A0 is 0, it selects the particular chip, and when BHE is 0, it will select the bank 1. So the use of A0 and the BHE helps us in selecting either the bank 0 or the bank 1. When both the banks are selected, we can directly access 16-bit of data. When only the odd bank is selected, we will be able to access the 8 bits at that odd address. When the bank 1 is selected, we can access the 8 bits or 1 byte which is at even address. If I say the addresses starts from the address of this memory, that is the address 1, the address 2, address 3, address 4, and so on. So looking at this table gives us some hint of how we can make use of the 8-bit or the 16-bit accessing. Look at the table, the BHE bar and the A0. BHE bar and the A0, which is asserted high, and BHE is asserted low. Let's see the combinations. When BHE bar is 0 and A0 is 0, so we will be able to access 16-bit of data That is, we can either read from the two banks or we can write simultaneously on two banks. So when the BHE is 0, so the bank 1 is selected. When A0 is 0, the bank 0 is also selected. Both the banks are selected and we will be able to access the 16-bit of data on the line D0 to D15. However, when BHE is 0, that means the bank number 1 is selected. When A0 is 1, so bank 0 is not selected. So with this one, the 8-bit of data will be read or written into the odd memory block. So bank 0 is odd memory block and bank 1 is bank 0 is even memory bank. So bank 0 is even memory bank and bank 1 is odd memory bank. So if you are to access from the even memory bank, starting address is 0. So with the starting address 0, that 0 is even number. So that will be in the bank 0 and this is when A0 is equal to 1. So that the chip is selected. Now when this chip is selected, the rest of the addresses from A1 to A19 will belong to the bank 0. So when A0 is 0 and now when A1 is 0, that means you have the address 00, that is an even address. When A0 is 0, the memory bank 0 is selected. When A1 is 1, so the address becomes 10, which is 2. So this address belongs to the memory 0 bank. But when you look at the BHE bar, when the BHE bar is 0, the bank number 1 is selected, and since the address being A1 to A19, now when A1 is 0, when A1 is 0, so A0 will be 1, so that will indicate the odd address of the bank 1, that is the first address of the bank 1. When the BHE is 1, this is not selected and the second one is selected. So that means the data from the even memory banks will be written or read into. When both are 1, 1, so neither this is selected nor the bank 0 is selected, so that will become as an invalid operation. So what have we seen is that by dividing the memory, by organizing the memory into the odd and the even, we are able to access either the 8 bits data or we can access the 16-bit data directly. And there is nothing that there is nothing that we lose anything by dividing or by organizing the memory into the two banks. Still the size of the memory remains same. But it gives us the flexibility whether we want to read from this bank, that is an even bank, or bank 1, which is an odd bank, or we read from both of them or write onto both of them. That is quite possible when we discuss that. So what we have seen that we can organize the memory into different banks so that we can access either only the 8 bits of data or 16 bits of data. But however, when we access using the even addressing, we can access both the even and the odd byte together, that is 16 bit at a time, and this speeds up the operation because in one cycle we are accessing we are able to read or write 2 bytes of information. So this accessing of the memory this way doubles the speed of the operations. Let's then see about the other address space. We know the address space is divided into the IO address space and the memory address space. The IOs can be in the form of the different ports, the different IO addresses. And the memory, of course, that is a physical RAM, ROM, etc. So we have 2 spaces, IO and the memory space. So IO space can, because we know that the 8086 has the 16-bit IO address as well, whereas the physical memory address is 20-bit. But when we consider or when we deal with only the IOs, the total address space is 16 bits. That means the number of IOs that 8086 can address is up to 64 kilobytes with 16-bit of IO addresses. And that IO space is totally an independent space. Now, to address to the IO space, we can have the in and the out instructions, which are used for either reading in or reading, transferring the accumulator content onto the IOs, that is the ports. And in each of these transfers, whether we are transferring from the port to the accumulator or from accumulator to the port, it is the AL or the AX register that will come into the picture. The content of the port 16-bit or the 8-bit is transferred either into the AL or into the AX register. Now, as contrast to the memory space, which was a total of 1 megabyte and was segmented for the ease of addressing, as the size of the total IO space is only 64-bit, and you have the registers which can contain 16-bit of address, there is no need for segmenting this memory. So this 16-bit of address, this can be fixed directly as part of the instruction. I can directly write as in from the port address, some 16-bit port address. So the data or the content from that particular port, addressed port, will come into the AL. Or I can write the instruction out at a particular port. Will transfer the content of the accumulator at that particular port. Or there is a provision that we can do it indirect way, and in which case the DX register is always used to contain the port addresses. So the activity then will be that we first load the DX register with the address of the port and then refer to in and out with the indirect way with the DX. So that the content of DX is nothing but they are the addresses, they point to the ports and the data can be transferred among the accumulator and the port. So this is what exactly the IO space is. Now when you deal with the IO space, the 8086 provides the flexibility of accessing them in terms of the IO mapped IOs or the memory mapped IOs. When you deal with the IO mapped that we saw in the previous slide, IO mapped, so you have the specific instructions for reading and writing into the IO space. But when we wish to make use of the memory mapped IO, the advantage is that we can use the same instructions. There is no need to have additional instructions for the IOs. The same normal read-write instructions for the memory can be used for accessing the IO space as well. So there is a flexibility, but this flexibility doesn't come free, so you have to pay cost for it. So also there is an advantage when you configure or when you organize the memory that way, that you can take advantage of the addressing modes which we discussed previously. That means there is no requirement for separate address calculation. The already available mechanism can be used for such kind of things. And the major advantage is that as long as the device responds like a memory component, the CPU doesn't know whether it is accessing from the memory or from the IO space. Unless you have separate instructions like the in and the out, wherein the separate reference is made. So in this case, the same instructions move can be used for transferring the data. So taking a recap, what we have discussed in this video was about the memory organization of 8086. We started with the pins which are useful in memory addressing, which are multifunction pins, but when you deal with after demultiplexing, you have the address pins A0 to A20. And with A0 to A20, we know that we can address 1 megabyte of the memory, but since the registers are not available for containing or holding that address, so some kind of segmented memory concept is introduced in 8086, which eases out the concept of addressing the 20-bit memory. Then we discussed that we can organize the memory into the different banks which contain only the even addresses, bank that contains only the odd addresses. Then odd addresses memory bank can be activated by the BHE, and the even memory address can be activated by the line A0. So this way we separate the odd address space and the even address space. And by using the signals BHE and A0, we can either enable both the banks, odd and the even bank, and access 16-bit of data, that is for read and write, or enable only one of the banks, even or odd, and access 8 bits of data, but in which case accessing 8 bits takes longer time for accessing. So whenever you need to read some bulk of data, it is always advisable to initialize your pointers to the even address boundaries. So this way we have discussed the complete concepts of the memory organization, and this memory can be organized as one physical device of 1 mega, or it is more advantageous to have it in two banks, bank 0 for even addresses, bank 1 for odd addresses. That's all in this video. Thank you.